Good morning student. Myself Sadanam Singh, lecturer electrical engineering from Government Polytechnic College, Mohali, Khunni Majra. To student, today's our topic is basics of electrical machines. In this lecture we will discuss the topic transformer. In this lecture we will discuss the overview of transformer, definition of transformer, principle of transformer, construction of transformer, transformer on no load and phasor diagram of transformer on no load, transformer on load and its phasor diagram, and different parts of transformer. So, what is transformer? A transformer is an electrical apparatus which transfer electrical power from one circuit to another at the same frequency. It can raise or lower the voltage in a circuit, but with the corresponding increase or decrease in a current. So, student, transformer is a device which transform power. It transforms power from one circuit, that is primary, to the another circuit, that is secondary. Transformer, it will either step up the voltage or it step down the voltage. You can see in this diagram that input voltage, that is primary voltage, is 220 volt and secondary voltage is 11 volt. So, in this diagram transformer is step down. It means that it step down the voltage from 220 to 11 volt in AC. So, if you see this diagram, current on the primary side is 0.5 ampere and on the secondary side is 10 ampere. So, student, it step down the voltage, but current is step up. So, it step up the current. So, from 0.5 ampere current step up to 10 ampere. So, step down the voltage according to the flux linking and number of turns. If you see on the primary side, number of turn is 44,400 and on the secondary side is 220. So, turns on primary side is more than turns on the secondary side. So, this transformer will step down the voltage. So, power input of this transformer is 220 into 5, 220 is the voltage and 0.5 is the current. So, if you multiply 220 into 0.5, we will get the power input, and that is 110 watt. On the secondary side, you can see voltage is 11 volt and current is 10 ampere. So, power again 110 watt. So, you can see that power remains same in the case of ideal transformer. Power remains same, but the voltage step down and current step up, and frequency remains same. If no power lost, then voltage that is transformed is from 220 to 11 volt and current transform is from 0.5 to 10 ampere. So, power will not lost. Power input, if power input is 110 watt, then output will also be a 110 watt. If there is any power loss, then secondary current will be less than 10 ampere and power will not that power that transformed will not equal, its magnitude will less than the input power. So, some power will lost in the transformer internal resistance. So, this is the simple diagram of transformer. Transformer basically consists of three main parts. First is this soft iron core and this primary coil and secondary coil. So, these three parts constitute the transformer. So, primary coil plus secondary coil plus core is equals to transformer. So, these three main parts form the transformer, which transform the power from one circuit to another circuit. So, electrical input electrical energy is applied on the primary side, and when input electrical energy is applied to the primary side, then current will flow through the primary coil. When the primary current flow, as you know, according to Faraday law of electromagnetic induction, whenever current flows through the coil wound over the magnetic material, then flux will produce. So whenever input electrical current flows through this primary coil, then magnetic flux will produce, and this magnetic flux will flow in the core as well as in the air. So the flux which flow in the core links with the secondary side, and whenever this flux links with the secondary side, then EMF will induce in the secondary coil and current will flow in the secondary coil. And the flux which links with the air is called leakage flux. That flux is not useful. Now, principle of transformer. The basic principle on which the transformer work is the electromagnetic inductions. Transformer consists of two independent windings wound over a laminated iron core which is built up of a thin sheet steel lamination to provide a path for a magnetic flux without any air gap. So transformer consists of two independent winding, that is primary and secondary winding, wound over a magnetic iron core. So this is the primary coil, and this is the secondary coil. When switch is in off position, then no current will flow and no power will transform from primary to secondary. When we close this switch, then current will flow in a primary winding and alternating flux will produce, which links with the this iron core. So whenever current flow through this primary coil, flux produced, this flux is alternating, and this flux linked with the iron core, and through iron core it links with the secondary winding. When this flux links with the secondary winding, uh, when this flux links with the secondary winding, an EMF will induce in this secondary coil, and current start flowing if load connected across the secondary coil. So whenever current flow through this coil, again another flux produced, which links with the iron core and with the primary as well as secondary winding. So transformer on AC supply. Transformer always used on AC, not on DC. The reason is for the production of EMF, two conditions required. First is flux linking, and second is flux changing. So flux linking, flux changing can be obtained only with the alternating magnetic field. In the case of DC, the magnetic field will not alternating, so flux will not produce any EMF in the secondary side in case of DC. So AC is used because it produces the alternating magnetic field in a soft iron core. Alternating magnetic field induced an alternating voltage in a secondary coil. In a transformer, the frequency of the primary and secondary remains same. So AC frequency in a secondary coil will equals to AC frequency in a primary coil. So this is the explanation of Faraday law. According to Faraday law, whenever a conductor cuts across the magnetic field, and EMF induced in the conductor. And second definition is whenever the magnetic flux linking with any circuit or coil changes, and EMF is induced in the circuit. So in this diagram you can see whenever the flux linking with circuit change, and EMF is indicating here that EMF is induced in the circuit. So same principle we use in the transformer, but here the flux changing is obtained with the alternating magnetic field. So in this case, flux is linking and changing with the motion of magnet. But in the case of transformer, flux is produced with the coil, and flux changing is obtained with the alternating characteristics of magnetic field. So input is AC, so magnetic flux that produced will also be a alternating. So alternating flux when links with the coil, and EMF will induced in the secondary coil also. So if you observe this diagram, the deflection in the galvanometer needle shows that EMF is induced in the coil. The direction of induced in the coil depends upon the direction of magnetic field and direction of motion of coil. EMF induced in the coil only when flux linking with the circuit change. So EMF will induced only when the flux links with the circuit change. If flux links but with, if the flux links with the coil but not change, then the no EMF will induce in this coil. So two conditions required. First is flux linking, and second is flux linking with the circuit should change. If you use the DC instead of AC, then what will happen? When DC current flow through the coil, again flux produced, but this flux, that magnetic field that is produced links with the core will not alternating, it will be a steady magnetic field. If steady magnetic field links with the secondary winding, then no induced voltage in the secondary coil, because it requires two conditions. First is flux linking, which is achieved. Flux linking is achieved, but second condition, flux should change. But if you use the DC supply, then flux changing will not be obtained. So flux link but flux not change, so no EMF will induced in the secondary coil. So if magnetic field decrease to 0, as secondary current decrease to 0. Voltage in a transformer. The voltage in a primary and secondary coil depends upon the number of turns in a coils. So whether we step up or step down the voltage, it depends upon the number of turns in the primary and the secondary. So ratio of number of turns and voltage, so ratio of voltage on the primary to secondary side equals to a number of turns on the primary and secondary. So if you increase the number of turn on the primary side, then it will step down the voltage. If you increase the number of turn on the secondary side, it will step up the voltage. Here you can see in the two types of transformer. First is step up transformer, second is step down transformer. Now stepped up transformer, number of primary terms in the primary side is less than the in the secondary side. So number of turns in the secondary side is more than the number of turns in the primary side. So it will step up the voltage. In step down transformer, number of turns on the primary side is more than the number of turns on the secondary side. So this line represents the core of the transformer. In the step up transformer, the secondary voltage is greater than primary voltage, and number of turns on the secondary side is greater than the number of turns on the primary side. In the step down transformer, voltage on the secondary side is less than the voltage on the primary side, and this achieved when number of turns on the secondary side is less than the number of turns on the primary side. So number of turns on the primary side is more than the number of turns on the secondary side. Construction of transformer. A simple form of transformer consists of two coils and laminated steel core. The two coils are insulated from each other and also from the steel core. The laminated core is built up of thin sheet of silicons. First is core type transformer. In core type transformer, the magnetic core is built up of lamination to form a rectangular frame. The lamination are cut in the form of L-shaped strip. The coils are wound on the two legs so that they fill the gap completely. So in the in core type transformer, core is made of two strips of the shape L, and they are stacked alternatively to reduce the air gap at the joint. So they form the core, and windings are wound on the two limbs of the core. Shell type transformer. In shell type transformer, the winding is sandwich type. In shell type transformer, the lamination are cut in the form of long strips of E's and I's as shown in figure. In shell type transformer, the core has three limbs, the two sides limbs and one center limbs. So shell type transformer are formed with the long strips in the shape of E and I. So these strips are again joined alternatively to reduce the air gap at the joint, and windings are wound on the center limbs only. Now, to understand the transformer, we will first discuss the ideal transformer. Ideal transformer means the transformer having no losses, but no transformer exists having no losses. An ideal transformer is one which has no losses, that is, whose windings have no ohmic resistance and no magnetic leakage flux. That is, all the flux produced in the core links with the both the windings, that is primary and secondary. In other words, an ideal transformer consists of two purely inductive coils wound on a loss-free core. Since there is no power loss, therefore output power must be equals to input power. The output power, that is V2 I2 cos phi, must equals to Vi cos phi in case of the ideal transformer. Means no power lost. The power at the that is input power is equals to the output power. So V2 upon V1 is equal to I1 upon I2 equals to K. K is the transformation constant. So if we draw the vector diagram, the voltage primary voltage is taken as a reference vector, and magnetizing current Im lags behind the voltage by angle 90 degree because it produces the magnetic flux, and this is the current of inductor, and the property of inductor is the current lags behind the voltage by 90 degree, and flux phi m is in phase with the current Im. EMF induced in the primary side, the magnitude of E1 is equal and opposite to the voltage applied voltage V1, and EMF E2 will in phase with the E1. The magnitude of E2 depends upon the number of turns on the secondary side. Consider an ideal transformer whose secondary is open and primary is connected to the sinusoidal alternating voltage V1. This primary voltage causes a current to pass through the primary winding. Since primary winding is purely an inductive coil, therefore the current lags behind the voltage by 90 degree. The function of this current is to set up an alternating flux in the core and magnetize it, hence it is called magnetizing current. The alternating flux links both the winding, that is primary and secondary, therefore it produces self-induced EMF in the primary. This self-induced EMF is equal to and in opposition to the voltage V1. When the flux links with the secondary winding, it produces mutually induced EMF E2 in the opposite direction to that of applied voltage. The magnitude of E2 is proportional to the rate of change of flux and number of turns. So first is the again the primary voltage is taken as a reference vector, and Im lags behind the voltage by an angle 90 degree. The function of this current is to set up the alternating flux in the core and magnetize it. The function of this current is to produce magnetic flux in the core and magnetize the primary winding, and flux in the same direction. EMF induced, the flux linking with the coil links with flux links with both primary and secondary winding. The flux linked with the primary winding produced an EMF in the primary winding, which is the magnitude of E1 is equal and opposite to the voltage V1, and this flux when links with the secondary winding produced another EMF, that is E2, and the magnitude of E2 depends upon the number of turns on the secondary side. Transformer on no load. When the transformer is on no load, that is when the secondary winding of the transformer is open circuit, and the primary winding is connected to the source, it takes no load current I naught. This current supplies the iron losses and copper losses in the primary. The primary copper losses are so small as compared to the core losses that they are neglected. It should be noted that there are no copper losses in a secondary side, as is it open. Primary current I naught is lag behind the voltage V1 by an angle less than 90 degree. Primary current has two components. First component is IW is in phase with the applied voltage V1. It is known as active or working component because it supplies the iron loss and small amount of copper loss. The other component IM is in quadrature with V1. It is called reactive or magnetizing component because it produces flux in the core and does not consume power. From the phasor diagram, working component IW is equal to I naught cos phi naught, and magnetizing component IM is equals to I naught sin phi naught. So if you draw the phasor diagram of transformer on no load, the reference vector is V1, and flux phi lags behind the voltage. Current IM lags behind the voltage by 90 degree, and flux will in the same phase. The no load current I naught lags behind the voltage by angle less than 90 degree. This I naught can be divided into two components. One component is IW. IW is in phase with the applied voltage, and it is known as active or working component because it supplies the iron losses and small amount of copper losses. Second component is IM. IM is the magnetizing component, and uh, uh, it produces the flux in the core. IM produces flux in the core and does not consume power. From the phasor diagram, we can see that IW is equals to I naught cos phi naught, and IM component is I naught sin phi naught. Transformer on load. When the transformer side of transformer is loaded, the secondary current I2 flows through it as shown in figure. The magnitude and phase of I2 with respect to voltage V2 are determined by the characteristics of load. This current is in phase with the secondary voltage V2. If the load is non-inductive, it lags. If the load is inductive, and it leads if load is capacitive. So when secondary side of transformer is loaded, current I2 start flowing in the secondary side. When the secondary side of transformer is loaded, the secondary current I2 flows through it as shown in figure. The magnitude and phase of I2 with respect to voltage V2 are determined by the characteristics of load. This current is in phase with the secondary voltage V2 if the load is non-inductive, and it lags if the load is inductive, and it leads if load is capacitive. So if we close the switch, first primary current flows in the primary coil, and it will produce the flux phi naught, and this flux will links with the primary as well as in the secondary side through the this core. So this flux is due to the growing primary current, and when this flux links with the this secondary winding, it will produce an EMF in the secondary winding, and current I2 start flowing in the through the load in the secondary winding. So when current I2 flows, then another flux that is phi 2 will produced in the secondary winding. When the transformer is on load, it primarily draws a load current I naught from the supply main. This no load current and MMF N1 I naught, which sets off flux phi naught in the core. So when current I2 flows in the secondary winding, it produces another flux phi 2, which links with the primary as well as secondary. So again, when we connect the supply to the primary winding, first current I naught will flows in the primary coil, and when current I naught flows in the primary coil, it produces the flux phi naught, which links with the primary as well as with the secondary. When it links with the primary winding, it produces the EMF E1, and when this flux links with the secondary winding, it produces the another EMF E2 in the secondary winding. So when we connect the load across this primary side, the current I2 will start flowing. When this current I2 flows, it produces another flux phi 2 from uh, from this secondary coil, and this flux will links with the primary as well as with the secondary. So this flux produce another EMF will and this flux will oppose the flux phi naught, and it tries to reduce the magnitude of flux phi naught. So to overcome at this moment, input supply take upper hand and it supply another current, that is I naught, I1 dash. This I1 dash when flows in the primary side, it produce another flux phi 1. The magnitude of this flux phi 1 dash is equals to the flux phi 2. So this and this flux 1 dash and flux 2 are equal and opposite, and they will cancel each other. Phasor diagram of loaded transformer. Since the voltage drop in both the winding of transformer are neglected, therefore V1 is equals to E1 and V2 is equals to E2. In the figure, vector are drawn for non-reactive load. Secondary current I2 is in phase with E2. It causes primary additional current I1 dash, which is in anti-phase with it and equal to its magnitude. Total primary current I1 is the vector sum of I0 and I1 dash and lags behind the voltage V1 by an angle phi. The magnitude of voltage V1 is equals to E1, and flux phi lags behind the voltage by angle 90 degree. Current I0 lags by the angle less than 90 degree, and magnitude of E2 equals to V2. Current I2 flow in phase with the E2, and current I1 dash is in phase with the V1. If we draw the resultant diagram, then the I1 is the vector sum of I0 and I1 dash. In this figure, vector are drawn for an inductive load. In this case, secondary current I2 lags behind the voltage E2 by an angle phi 2. Current I1 is in anti-phase with I2 but in equal in magnitude to it. As before, I1 is the vector sum of I0 and I1 dash and lags behind V1 by an angle phi 1. So in the case of load is inductive, current I2 lags behind the voltage E2 by an angle phi 2, and I1, which is in opposite equivalent opposite to the I2 is drawn opposite to the I2, and total current I1 is the vector sum of I0 and I1 dash. So in case we use the capacitive load, then the current I2 I2 leads the voltage by an angle phi 2, and I1 dash antiphase with the I2, and resulted